Okay, in Chem 20, you will have calculated the pH of strong acids because they 100% ionize. Now, this is part of our equilibrium unit, and that means that we're going to focus on weak acids and weak bases because they don't 100% ionize, but they only partially ionize. They exist in an equilibrium. And so we have this other thing that we have to do because we can't do the stoichiometry. Just like when we were calculating Kc values, we had to write an expression and then plug in our values and then get our answer because we couldn't just directly do our stoichiometry because it wasn't a quantitative or 100% reaction. So here's some examples. If I take ethanoic acid, like vinegar, in water, it exists in equilibrium. So this is what its equilibrium looks like. So here is our Bronsted-Lowry acid. It donates a proton to our water, which is our Bronsted-Lowry base, and it forms these conjugates, your H3O plus and your CH3COO minus. So you have this Bronsted-Lowry acid, Bronsted-Lowry base, conjugate acid, and conjugate base. Okay, so we can write an equilibrium expression for this. Products of a reactants. Here are my products. Here are my reactants. I didn't include water because it's liquid, right? This is a heterogeneous equilibrium, and so I have two different kinds of states, so I only include the aqueous. So did you see how this is all tying from last unit as well? Or last chapter, I mean. Okay, so products of a reactants, not including water because water is a liquid and I've only included the aqueuses. Now this is a special kind of K. This is not just Kc, for C for concentration, but it's a special kind called Ka. And Ka is when you have a weak acid in water. So the weak acid solution. So this is a vinegar solution, right? So it's your weak acid in water, gives you your K, gives it a special kind of Kc called Ka. And in Ka, you always end up forming your H3O plus and your conjugate base over your weak acid. Now in your data booklet, which I had a data booklet right here 2 seconds ago. In your data booklet, you have a whole page of K values. Oh, there it is. So you have a whole page of K values, right? Ka values. So here's your acid and base table where these are your strong acids. Do you remember that? So here you have all of your Kas for your weak acids. The Kas are very large, as in like 1 for your strong acids because they 100% ionize. So this Ka for vinegar is just right off of the data booklet, and it says that it's 1.8 times 10 to the power of -5. A really small Ka value, right? 0.000018. And so that's super small, meaning this is very little and this is large, meaning this is very little and this is large. Okay, so let's just do one a little bit faster here. Here is the the Ka expression and value for methyl. What's an indicator? So in that indicator list, this is the methyl. This is phenol red. I was going to say phenol red, and then I was like, I didn't remember phenol red. Okay, so this is for phenol red. So in your data booklet on page 10, you have a list of indicators. Those indicators are, look, weak acids and their conjugates. And so we have here, like, for example, I'll just read the top one. So it's methyl red, HMV is the weak acid, MV minus is the weak base. It's not really MV. There's no such thing as MV. That's just an abbreviation for like a really big complicated molecule. When you have HMV, its pH range is 0. When you have MV minus, its pH range exists. So that equilibrium lies where it favors the MV minus if the pH is larger than 1.6. The color of HMV is yellow and the color of MV minus is blue. So for here, we have our phenol red. So this exists in 6.6 and it favors this side of the equilibrium with a pH of above 8. This is red and this is yellow in color according to your data booklet, okay? All right, so there's the expression, products of a reactants. I didn't include liquid water, right? It's not there. And the value that's in your data booklet for the Ka for this is 1.8 times 10 to the power of -8. Okay. So let's get into some math part then here. So now that we've set up what a Ka value is, it's a weak acid in its base, products of a reactants, that indicators are weak acid, conjugate base table as well. Okay, so predict the H3O plus and pH for a 0.075 mole per liter solution of benzoic acid. So just a reminder about what benzoic acid is, right? It's a benzene ring with a carboxylic acid group attached to it. And here it exists in equilibrium. So the benzoic acid in water. So because I'm looking for H3O plus, the only thing that's there is a solution. Those are your two species. So there's my two species. Over, there's my conjugate base and conjugate acid. So of course, with a weak acid, I'm forming my H3O plus. Now this, it doesn't look like a nice table, but this is a nice table. So when it says that I have that mole per liter, this is actually my initial concentration of my acid. So here I have an initial concentration. I started with 0, It's going to change by an X value, change by an X value, change by an X value. And so at equilibrium, I'll have 0.075 minus X, X, and X. And the question says, what is the H3O plus concentration? It means at equilibrium. And then what is the pH? So the first thing I need you to do is I need you to recognize all of the hidden things that are in this. And number one, it doesn't look like a nice table, but it is. Number two, this is supposed to be an I value, but it doesn't really look like it. Doesn't say it placed in or whatever. And then number three, when it asks for that, it's looking for the equilibrium, not just here. Okay, so all those little things to worry about. Okay, so then I can create my K expression, products of a reactants without water. This equals this, that's from the data booklet, right? And then that's going to equal my X's multiplied by each other minus, or divided by that 0.075 minus X. Okay, so now we have this thing called an assumption rule. The assumption is that this is such a weak acid that this value is so small that I'm hardly going to have much of a change in this 0.075. So solving for X right now leads me to a quadratic. You are going to have to use a quadratic in university, but in Chem 30, I don't expect you to be able to use a quadratic. So because you should be able to take Chem 30 without taking Math 30. So okay, so you don't have to do the quadratic equation to solve for this. We're just going to assume that this changes by an insignificant amount. So 0.075 minus 0.00001 is insignificant, and it's going to round anyway to be our 0.075. So because that's insignificant, I can delete it. Okay, so the golden rule is if you don't have X, you can assume 0. If you have X, please plug it in, okay? If you have X, use it. So if you have it, use it. If you don't have it, you can lose it. Okay, so what I end up with is this. Approximately the Ka value, which I got from the data booklet, equals X squared from that X squared there, divided by the total initial concentration. Okay, so then plug that in, solve for X, and your X equals 0.00217 moles per liter is my H3O plus concentration. So the hydronium ion concentration at equilibrium ends up being 0.002 moles per liter. Converting that into the pH, now I can use my Chem 20 formulas. Now I finally know how much H3O plus I have in there. Because it was a weak acid, I had to do the Ka first, find my H3O plus concentration, and now I can plug it into the pH formula. So pH equals negative log hydronium ion concentration, which equals negative log of that little tiny value that I just found, which equals my pH of 2.66. So a weak acid pH. So I must have been on the right track anyway. So what has this got to do with percent ionization? Okay, if I had my weak acid, my benzoic acid and water giving me my 2 ions, and if it was 100% ionization, then it'd be like it was in Chem 20, where I have, look, if I have a 0.075 mole per liter solution I will get a 0.075. It'll dissociate 1 to 1, right? That this will dissociate or ionize, because it's an acid, sorry, ionize as a 1 to 1. And so if I have 1 mole per liter, I'm going to get 1 mole per liter and 1 mole per liter. If I have 0.075, I'm going to get 0.075. But I didn't get 0.075. I got 0.002. So my 75 was actually 0.002. I went from 75 to 2 moles per liter. So in Chem 20, I would have predicted 75. And now I'm saying, no, the Ka value here shows me it's only 2%. Not 2%, I mean only 2. So I was supposed to get 75 and I only got 2. That's a lot, that's not a very good percent. So what I'm going to think about it is like on a test. So if I was supposed to get 75 and I actually only got 2 on that test, what was the percent on that test, right? So I actually only got this. If I was at 100%, I would have got this. And so the mark that I got over the mark that I should have got, or if it was 100%, I would have got. And so my percent is only 2.9% equilibrium. So that means that over top of this arrow, I could write a 2.9%, meaning only 2.9% of this is converted into this, and the rest of it stays like this. That's why we could assume that that X was 0, because most of it stayed as that molecular compound anyway. So it was basically still a concentration of 0.075. Okay, let's try one more example. Okay, so what is the concentration of a hypochlorous acid solution with a pH of 4.87? So for this one, I've given you the pH, and we're going to go backwards, and we're going to find the acid concentration. So from the pH, we can then use our Chem 20 formulas, and we can figure out the H3O plus concentration. So H3O plus equals 10 to the power of negative pH, which is this value, or this value. You can use this long value in your calculator too, 1.3 times 10 to the power of negative 5 moles per liter. I'm going to just use this because it just looks neater on the board. What does it look like? So here it is in solution, my hypochlorous acid in water, donates proton. I get my hydronium ion concentration, of course, and the conjugate base. So my Ka looks like this, the value out of the data booklet, and then products over reactants, but not water. Okay, so here I'm just going to pause something because last question we did an ice table. So here's the ice table, right? I is what I'm looking for. Change column is all my X's. E is going to be the I minus the X. Then I have that calculation that I just figured out. You can't really see that, hey? Hold on a minute. Let me do that. Here. So then I have 10 to the power of, and then I have 10 to the power of, okay? So if I were to plug this in, I would get this squared, right? So that's squared over, so that's squared, here we go. So this squared over I minus this, over I minus this. But you know, because a weak acid is always ionizing by 1 and 1 and get your conjugate base, and I end up with a very generalized formula that every time I do this, I end up with my X squared divided by I minus X, where X is equal to my H3O plus concentration. So I'm actually going to use that general formula right there. I'm going to use that general formula from here on in, where I have Ka equals X squared divided by, okay? So right now, let me just zoom out again. Right now I have my Ka equals the expression. I'm not going to do an ice table. You can do an ice table if you want. Like, some people feel really comfortable with ice tables. So I wrote the equation, I wrote this, and I know that whether I do the ice table or not, I'm going to come up with the Ka equals X squared divided by I minus X. Those two numbers squared divided by I minus that number, okay? So now I just have some algebra. Number equals a bunch of numbers with one unknown. I am not allowed to lose this because I have it, right? If you have it, you use it. So I have it, so I'm using it. And so distribute, FOIL, square, algebra, presto, and you get I equals 0.00456. I believe in my answer key I have 45, so I'll have to change that. But anyway, 0.00456 moles per liter for I, the initial concentration of this acid. So what is the concentration of the hypochlorous acid? It is that answer. Okay, so that's Ka. You have to first see, is it a weak acid? If this is a weak acid, You ask yourself, is this a weak acid? Then I have to first do my Ka before I can do my Chem 20 formulas, my pH formulas. Whereas if you looked at it and it was a strong acid, and that might happen, then you don't use your Kas, you just right away go ahead and use your Chem 20 formulas. Okay, so that's calculating pH of a weak acid.